After we finish the forces acting on particle moving in magnetic fields or on current carrying wire, now we will deal with the magnetic fields due to currents. First case is the magnetic field due to current carrying wire. When the wire carries a current, the alignments of the iron flings show that the magnetic field induced by the current forms concentric circles around the wire. Also here compasses can be used to show the direction of the magnetic fields induced by the wire. So when the current is moving inside the wire, we will have magnetic field around the wire, which is make circle around the wire. Here we can use compass to show the direction of the magnetic field, which is circles. Now we will use the right hand grip rule to find the direction of the magnetic fields. Right hand grip rule can be used to determine the direction of the magnetic field for current carrying wire. If the wire is grasped in the right hand, the direction of the thumb will represent the direction of the current, and the direction of the four fingers will represent the direction of the magnetic fields, as shown in the following figure. The magnetic field strength generated by current carrying wire can be calculated by the following formula. B equal mu 0 I divided by 2 by R. B is the magnetic field strength induced around the wire. Mu 0 is the permeability constant, which equal 4 multiplied by pi 10 power minus 7 Tesla meter per ampere. I is the current in ampere. R is the distance between the wire and the point where we want to find the magnetic field strength in meter. Example 7. Depending on the values in the figure, find the magnitude and the direction of the magnetic fields in the points A, B, and C. Okay. Now to find the magnetic field strength and direction in A, B, and C, we need first to find the direction, then we need to calculate the magnetic field from each wire separately. Okay, regarding the magnetic field direction, for the wire number 1, in the right side, the direction will be X, in the left side will be dot, because the magnetic field is making circle around the wire, is moving like this. From here it's going outside and here is going inside. Okay, for wire number 2, the magnetic field lines is going like this. So here is dot and here is X. So in point A it is in the left side of wire 1, so it will be dot from B1. Also left side from wire 2, so it will be X from B2. Now we determine the direction of the magnetic field from each wire. After that, we need to find the strength of magnetic field. So in point A, B1 equal mu 0 I1 divided by 2 by R1. Mu 0 is constant and I1 is 1 ampere. R1 is the distance between the wire number 1 and the point where we want to find the magnetic field. So it's 2 centimeter. We convert centimeter to meter. So it will be 2 multiplied by 10 power minus 2. By with by cancel. 2 multiplied by 2 is 4, cancel with 4. So the answer will be 1 multiplied by 10. This one power minus 2, we move it up, so it's become positive 2. Minus 7 positive, and we have positive 2, which means minus 7 plus 2 will be minus 5. The unit of magnetic field strength is Tesla. So this one B1. B1 have direction of positive Z. So we need to mention the direction here. Now for B2 equal mu 0 I2 divided by 2 by R2 equal. Mu 0 is constant for air or vacuum. I2 is 2 divided by 2 by R2 is the distance between the second wire and point O and point A, which is 2 multiplied by 4 is 6. 2 plus 4 is 6, plus 2 will be 8 centimeter. So this one 8. Then we convert centimeter to meter, so it will be 8 multiplied by 10 power minus 2. By with by cancel. 2 multiplied by 4 is 8, also cancel. So the answer will be half. Now 10 power minus 2, we move it up, so it will become 10 power minus 5. Tesla. The direction of magnetic field for B2 is X, which means negative Z axis. Okay, the direction of magnetic field is opposite. One is positive Z, one is negative Z. So to find the resultant magnetic field in A, we say BA will equal the highest minus the lowest. So it will be B1 minus B2 because the direction of magnetic field will follow the direction of the highest magnetic field. So it will be 1 multiplied by 10 power minus 5 minus half multiplied by 10 power minus 5. So the answer will be 0.5 multiplied by 10 power minus 5 Tesla with the highest, which means dot or positive Z axis. Okay, this one BA. Now we need to find B. So N point B. Now also here we need to find B1 and B2. B1 equal mu 0 I1 divided by 2 by R1 will equal 4 multiplied by pi multiplied by 10 power minus 7, which is mu 0, multiplied by current number 1, which is 1 ampere, divided by 2 by R1. Okay, let me change the color. Now, the distance between I1 and B1 is this one R1, and R2 is the distance between I2 and B, this one R2. So here R1 it will be 4 centimeters, so 4 multiplied by 10 power minus 2. Pi with pi cancel, R with 4 with 4 cancel. So the answer will be half multiplied by 10 power minus 5 Tesla. Now let's determine the direction. The direction of magnetic field from B1 is X. From B2 is X. So both have the same direction. B2 will equal mu 0 I2 divided by 2 by R2. It will be 4 multiplied by pi 10 power minus 7. I2 is 2 ampere divided by 2 by multiplied by the distance, which is 2 centimeter, By with by cancel. 2 multiplied by 2 is 4. So the answer will be 1 multiplied. Sorry, we still have 2. So the answer will be 2 multiplied by 10 power minus 5 Tesla. Also the direction is x. So B at point B, because both in the same direction, we add them. So B1 plus B2. So the answer will be half multiplied by 10 power minus 5 plus 2 multiplied by 10 power minus 5. So the answer will be 2.5 multiplied by 10 power minus 5 Tesla, and the direction is x. This one at point B. Now, at point C. Okay, for point C, let's determine the direction first. From B1 is x, from B2 is dot. So here we need to subtract them. So first let's find B1 and B2. B1 equal mu0 I1 divided by 2 by R1. Mu0 is 4 multiplied by multiplied by 10 power minus 7. I1 is 1 ampere. 2 multiplied by multiplied by R1. Okay. Let me change the color. First, we make it green. The distance between point C and current number 1 is 4 plus 2 plus 2, which means 8 centimeter. And the distance between current 2 and C is just, this one R2 is just 2 centimeter. So here R1 is 8 multiplied by 10 power minus 2. Okay, 4 with 8 cancel, we still have 2. By with by cancel, so the answer will be 1 divided by 4 multiplied by 10 power minus 5 Tesla, and the direction of B1 is x. Now B2 will equal mu0 I2 divided by 2 by R2, which equal 4 by multiplied by 10 power minus 7 multiplied by I2, which is 2 ampere, divided by 2 by, okay, R2. Now R2 also 2 centimeter. By with by cancel. 4 cancel with 2 multiplied by 2. So the answer will be 2 multiplied by 10 power minus 5 Tesla. And the direction is, for B2 is dot. Now to find the resultant magnetic field, we say B at point B will equal the highest, which is B2 minus B1, which equal 2 multiplied by 10 power minus 5 minus 0.25, which is a quarter, multiplied by 10 power minus 5, which equal 1.75 multiplied by 10 power minus 5 Tesla, with the highest. The highest is B2, so the direction will be dot. So this is the answer for the finding the magnetic field in points A, B, and C. Example 8. Depending on the values in the figure, find the magnitude and the direction of the magnetic field in point A. Okay. First, the direction of magnetic field from current number 1. Right side is x, left side is dot. For the second current, right side is, down here is X, up is dot. Because as we mentioned before, the direction of magnetic field is moving like this. Also here is moving like this. So this will be dot here X. Now, in point A, the magnetic field from wire 1 will be X. From wire 2, it will be dot. So now we need to find B1 and B2. Then we need to subtract the highest value from the, highest value minus lowest value. Okay. B1 equal mu 0 I1 divided by 2 by R1, which equal 4 pi multiplied by 10 power minus 7 multiplied by current number 1, which is 1, divided by 2 pi R1, which is 4 millimeter. Now to convert millimeter to meter, each 1 meter have 100 centimeter, and each 1 centimeter have 10 millimeter. So each 1 meter will have 1000 millimeter. So to convert from millimeter to meter, we divide by 1000. So 4 multiplied by 10 power minus 3. So to convert from millimeter to meter, we divide by 1000. Okay. Pi with pi cancel, 4 with 4 cancel. So the answer will be half multiplied by 10. Minus 3 is going up, so it's become 3. 3 minus 7 will be minus 4 Tesla. And the direction of B1 is X. Now for B2 equal mu 0 I2 divided by 2 by R2. Mu 0 is constant. Current 2 equal 2 ampere. R2 equal 2 millimeter. Pi with pi cancel. 2 multiplied by 2, 4 is cancel. So the answer will be 2 multiplied by 10 power minus 4 Tesla. And the direction of magnetic field from the second wire is dot. So now B at point A will equal B2 minus B1, which equal 2 multiplied by 10 power minus 4 minus 0.5 multiplied by 10 power minus 4. So the answer will be 1.5 multiplied by 10 power minus 4 Tesla. And the direction of magnetic field is with the highest. The highest is B2, so the direction will be dot. Example 9. Depending on the values in the figure, find the magnitude and the direction of the magnetic fields in points A and B. At point A, we have two magnetic fields, one from wire and the second from the original magnetic field, which is 2 millitesla. Now, first we need to find the magnetic field from wire. So at point A, B wire will equal mu 0 I divided by 2 by R, which equal 4 pi multiplied by 10 power minus 7 multiplied by current, which is 2 ampere, divided by 2 pi multiplied by the distance, which is 0.2 milli. We convert milli to meter, so we multiply by 10 power minus 3. Okay. Pi with pi cancel. 2 with 2 cancel. 0.2 with 4 cancel. This one we will have 2, and because of point we will have 20. and 10 power minus 3, we move it up, so it's become positive 3. So the answer will be 20 multiplied by 10 power minus 4. The unit is Tesla. The direction is positive x. So B at point A will equal B original plus B wire, because both in the right side. From wire, okay, the direction of magnetic field at point A from wire is will be to the right. This one be wire, because the direction of current is inside the page, so the direction of magnetic field will be to the right at point A, this one. So B original is 2 multiplied by 10 power minus 3, and B wire is 20 multiplied by 10 is power minus 4. We make the power same, so 2 multiplied by 10 power minus 3 plus, we cancel this 0, and we change this one to minus 3. So it's become 2 multiplied by 10 power minus 3. So the answer will be 4 multiplied by 10 power minus 3 Tesla, and the direction is positive x. So this the magnetic field at point A. For point B, the original direction of magnetic field is to the right. This one B original. And the direction of magnetic field from wire is will be to the left. So this one B wire. So here we need to subtract the two magnetic fields from each other. So at point B, B wire will equal mu 0 I divided by 2 by R. It will be the same, because the same distance, the same current, everything the same. So it will be 20 multiplied by 10 power minus 4 Tesla, but the direction is to the negative x-axis. Okay, this one B wire. Now, to find the magnetic field at point B, so B at point B will equal. Which one is the highest? Actually, both are the same, because the magnetic field from wire is 2 multiplied by 10 power minus 3 Tesla. And the original magnetic field also the same, 2 multiplied by 10 power minus 3. So here, both are the same and in opposite direction. So the answer will be 0, because if we say B original minus B wire, or B wire minus B original, in both cases the answer will be 0, because the two magnetic fields are the same and in opposite direction. So the net magnetic field or the resultant magnetic field will be 0. So at point B, there will be no magnetic fields. The magnetic field strength will be 0. Example 10. Depending on the values in the two figures, find the points where the magnetic field strength equal 0. Okay, we have two cases. The first case, the two currents are parallel in the same direction, while for the second case, the current in opposite direction. Here, if the two currents are parallel in the same direction, the point where the magnetic field strength equals 0 will be between them and near the lowest current. So it will be in this position, between them and near the lowest current. While if the currents are opposite, the point where the magnetic field equals 0 will be outside and near the lowest source will be in this position. So for case number 1, this one case number 1, this one case number 2. In case number 1, at this point, the magnetic field strength equals 0. Why? Because the direction of magnetic field from the first wire, which is B1, will be inside the page, while the magnetic field from wire number 2 will be outside. Because both magnetic field are in opposite direction, so they cancel each other. Okay, when magnetic field will be 0, when B1 equal B2 in magnitude and opposite in direction. So here, for case number 1, B1 must equal B2 in magnitude and opposite in direction. So mu 0 I1 divided by 2 pi R1 will equal mu 0 I2 divided by 2 pi R2. Mu 0 with mu 0 cancel, 2 pi with 2 pi cancel. So I1, which is 1 ampere, divided by R1. R1 is this distance, and this distance is R2. So R1 will equal I2, which equal 2, divided by R2, which equal R2. So by cross multiply, 2R1 will equal R2. Okay. Here, from the graph, R1 plus R2 will equal 6 centimeter. So we can say that R1 equals 6 minus R2. So here, instead of R1, we can say 2. We can replace R1 with 6 minus R2 will equal R2. Then we will have just one variable, which is R2. 2 multiplied by 6 is 12, minus 2R2 will equal R2. We move this one here, so 12 will equal 3R2. We divide both sides by 3. So R2 will equal 4 centimeter. So R2 is 4 centimeter. Then R1 will equal 2 centimeter. So here we determine the position where the magnetic field equal 0. For case number 2 is the same. We say B1 equal B2, which means mu 0 I1 divided by 2 by R1 will equal mu 0 I2 divided by 2 by R2. Mu 0 with mu 0 cancel, 2 by with 2 by cancel. I1, which is 1, divided by R1. R1 is this one, so R1. I2 is 2, divided by R2. R2 is this distance, this one R2. So cross multiply, 2R1 will equal R2. Now here, R1, okay, we can say R2 equal 6 plus R1. Because the distance between two wires is 6 centimeter, and the point where the magnetic field is 0 is in this position. So R2 will equal 6 plus R1. So R2 equals 6 plus R1. So here 2R1, we replace R2 by 6 plus R1. Now we move R1 here. So 2r1 minus r will equal 6. 2r1 minus, so this one r1, 2r1 minus r1 will equal 1r1. So r1 will equal 6 centimeter. So this distance is 6 centimeter. So r1 6 centimeter, r2 will equal 6 plus 6, which equal 12 centimeter.